Welcome back to 5-Minute Chemistry. Today we are going to discuss another method to enumerate electrons in covalent bonds, which is the oxidation number. So the issue we find ourselves in is that the electrons in covalent bonds are very important because the rearrangement of the electrons around the atoms is what drives chemical processes. So we should have some simple ways to describe the places of electrons accurately enough so we can explain the chemical reactions that materials take part in. And the formal charge does not describe really well what the electronic structure of molecules and polyatomic ions are. So we need to have a way to describe polar bonds in a simple way, which is not as complex as quantum mechanics, but also gives us an accurate enough description of what's going on. And for that, let's take a look at these three molecules. All of them contain chlorine, but chlorine is bound to different elements here. So if chlorine is bound with fluorine, so fluorine has the highest electronegativity of all the elements in the periodic table, so it will grab on the electrons in the covalent bond stronger than the chlorine and will have a partial negative charge, and the chlorine will have a partial positive charge because of the difference in electron density. In the other molecule here with chlorine and iodine, chlorine will have the higher electronegativity, so chlorine will grab on the electrons in the bond stronger and will have a partial negative charge, and iodine will have a small positive charge on it. And of course in the Cl2 molecule, when two chlorine atoms are bound together, the electrons in the bond will be actually shared equally between the two atoms. But if we wanted to describe this with the formal charges, well, by dividing up the bonds 50-50, we would actually end up with a formal charge of 0 for all of these atoms here. So instead we can introduce the oxidation number, in which we are not breaking the bonds in our imagination equally, but instead we imagine ionization. So the atom with the higher electronegativity will grab all the electrons from the bond and ionize the other. So fluorine will take all the 2 electrons from this bond when it's bound with chlorine, and when chlorine is bound with iodine, then chlorine as the higher electronegativity atom will take both of these electrons from the bond here, and when chlorine is bound with another chlorine, their electronegativity is the same. So in this case we can just divide up the bond one by one. So the oxidation number will be the charge of the atom, or rather the ion, if we would do this ionization. So this is kind of an exaggeration, of course, of the polar covalent bond by this enumeration. So here with ClF, chlorine will have a +1 oxidation number because it lost 1 electron. It only has 6 valence electrons instead of the 7, while fluorine has 8 valence electrons instead of the 7, so it will have an oxidation number of -1. In Cli, the 2 electrons are going to chlorine, so chlorine will have 8 valence electrons instead of 7. Here, chlorine became the negatively charged ion in our imagination with its 8 valence electrons, and iodine has the +1 oxidation number. And when it comes to the Cl2 molecule, then both of the chlorine atoms will have 0 oxidation number because they both kept their 7 valence electrons there. And basically oxidation number in elements will always be 0 because of this. So let's take a look at the difference between formal charges and oxidation numbers in the thiocyanide anion, for which we previously already looked up the formal charges. So now let's take a look at the oxidation numbers. The electronegativities of these atoms will be very important. So nitrogen has the highest electronegativity, so it will get all the electrons from the bond with the carbon. That means 8 valence electrons for nitrogen. So nitrogen as an element has 5, now it has 8. So oxidation number is -3, which is the same as the anion would be. So if nitrogen would form its natural anion, that would be the nitrite anion with 3- charge, and that is the oxidation number for nitrogen here. Carbon and sulfur has very similar electronegativities, and I've seen on the internet that some people would just divide this bond half-half, but I think it makes sense to assign all these 4 electrons in the bonds to sulfur, because if we do that and sulfur gets the 8 electrons, which is 2 more than it originally had, it will have the -2 oxidation number, which corresponds to the charge of the natural anion it would form. So sulfide anion would have the -2 charge over there. So our last remaining atom here is the carbon, which does not have any valence electrons left, but the elemental carbon, the carbon atom has 4, so it has +4 oxidation number. And based on this, we can kind of have an idea of the polarity of the two bonds here also. Okay, let's take a look at another example. Here we will compare the three ways of enumerating the electrons. One is for the octet rule, and then formal charge, and then oxidation number, and this will be carbon monoxide. So when carbon and oxygen bound together in this diatomic molecule, this is the structure we will have, a triple bond between the two atoms and two non-bonding electrons on both of them. Let's not forget that the triple bond has 6 electrons in it. And then let's consider the octet rule. In the octet rule, the 6 electrons in this triple bond will be counted to both of the atoms. When we take a look at how the formal charge works, then we of course just divide the 6 electrons in the triple bond half-half. So 3 electrons go to carbon and 3 electrons go to oxygen. That means carbon now has 5 valence electrons and the -1 formal charge, and oxygen also has 5 valence electrons, but it will have +1 formal charge. For the oxidation number, we will assign all the electrons in the bond to oxygen, because oxygen has higher electronegativity than carbon. And by assigning all these 8 electrons in total to oxygen, oxygen will have -2 as its oxidation number, and carbon will have +2. So here we can see that the oxidation number and the formal charge actually has the opposite sign for these two atoms. This is not really a usual case, but sometimes it happens, and it shows us that the Lewis structure is indeed not really perfect. So based on just this information, it would be very difficult to tell whether the carbon atom or the oxygen atom has the negative polarity in this molecule. So you either have to do some experimental evaluation or go to quantum mechanics to find out. And if you do some experiments, you'll find that the carbon atom will have the partial negative charge. Okay, this is it for today, and I will see you next time.